Okay, so just quickly revise yesterday. The limit notation. We talk about a function, f of x, and what's happening to it when x gets closer to a value. So the limit as x tends to a. So what's happening to f of x when x gets closer to a? And that's our limit notation. And when you have a graph, it might be something like that. That's a cubic graph. And I might be saying, what's the limit here as x? So if this is a, and as I come along the graph this way, what value is that getting close to? And as I come along the graph this way, what value is it getting close to? Okay, and how we do that is we just sub in, that's usually equal to f of a. Okay, we just sub in the value for a. So if I'm getting the limit of 3x squared minus 2 as x tends to 2, I would just do that's 3 times 2 squared minus 2, which is 3/4 12 minus 2, that's equal to 10. Where that runs into difficulty is if we have rational functions. So if I had something like x squared minus 3x plus 2 over x minus 1, and I want the limit as x tends to 1. If I sub in 1 there, I get 1 minus 3 plus 2 over 1 minus 1, which is 0 over 0. And I can't divide by 0, so I can't work that out. So what do I do in that case? Anyone? What do I do if I end up with 0, 0 when I sub in for my limit?
Do you factorize the top of?
Yeah. So try and factorize. So we have the limit now as x tends to 1. Factorize that for me. And you're hoping that this will be one of the factors anyway. So, Aaron, Zeph, can you factorize that for me at the top? Your mic working?
Would it be -1 and -2?
Thanks, Andre. Yeah, x minus 1, x minus 2. So what you do is you look at the factors of 2, which are 1 and 2, and you want them to add to give -3. So they're both, if they're both, because this is plus, they're both negative, or both positive because this is minus, it tells us they're both negative. And now we can cancel that out. So now we've got the limit as x tends to 1 of just x minus 2. So that's equal to 1 minus 2, which is equal to -1. So when you're asked to get the limit as x tends to a number, you just sub in that number and work it out. If you end up with a 0 in the denominator and you can't work it out, see if you can factorize. And sometimes you can't factorize. Sometimes there is no limit. Okay? And then to see if a function is continuous or not, so sometimes functions have jumps in them. So you may have, they're what's called piecewise functions. So you might have a function that's kind of going like this, and then suddenly it jumps up to here, okay? So in that case, the limit, we can have a limit coming from the left. So as x tends to a, you could say from the negative direction, and then you could have the limit as x tends to a from the positive direction. So we can have limits coming from 2 different directions. So say this is 5, and this is 8, and this is 3, okay? And this is my graph of f of x. It just happens to be in 2 different parts. So the limit of f of x as x tends to 3 from the negative direction is equal to, so I'm coming along from the negative direction where x is negative, approaching 3, my limit at 3 is equal to 5, okay? When I'm coming in the positive direction, the limit as x tends to 3 from the plus direction, coming along from the plus direction, and I see the limit as 8. So if those two limits are not equal, so the limit as x tends to a from the minus does not equal the limit as it comes from the other direction, that means it's not continuous. Does that make sense?
Yeah.
Miss, does if it's going up doesn't not mean it's plus though, like in down negative.
You mean this here?
Yeah, like you know the way you're saying, like how come it's not like the other way around? Because like
it's basically this little tells you which direction you're coming from. So I'm coming from the left or coming from the right. Negative usually means this way, this side if you like, and plus means this side. And yeah, you would think it's negative going that way, but it's just saying it's from the negative side.
so it doesn't matter if it's up or down.
What do you mean up or down? No, it just
Like this
if it was coming down like this.
Yeah.
No, what that means is I'm coming from the left, and this means I'm coming from the right, basically.
Okay.
Okay. So negative means to the left, positive to the right. So if I'm coming along the function from the left, my limit as I get closer to 3 is going to be 5. If I'm coming along from the right, it's going to be 8. And if they're not the same, obviously there's a break in the function, so it's not continuous. Okay?
Yeah.
So that's basically what we were looking at yesterday, the limits. And the whole idea of limit is looking at a function, what's happening closer and closer to value. Now, one of the very important ones that we came across is the limit as x tends to infinity. And what we call this is the end behavior of a curve. And by end behavior, it means what's happening at either end of the x-axis, okay? So that could be going to plus or minus infinity. So if you have a curve like an exponential, so say it was a decreasing exponential, okay? So there's our f of x. And I say the limit of f of x as x tends to infinity. Well, here I can see it's getting closer and closer to 0. Okay, so that's equal to 0. And one of the key things is, one of our most important functions is the limit as x tends to infinity of 1 over x or of anything over x. So as x gets bigger and bigger and bigger and bigger, what happens when you're dividing a number by x? What does that get closer and closer and closer to? So if you divide a number by something that's much, much bigger than it, what's your answer going to be?
Zero.
Yeah, thank you. Okay, like just take out your calculator. If I do 50,000 divided by 6 by 10 to the power of 100. Yeah. Right. 6 by 10 to the power of 100. Our calculator can't even handle it. So if I do 5 divided by 100, I get 0.05. If I do 5 divided by a much bigger number, like a million, I get 5 by 10 to the minus 6. So that's 0.005. If I make this number even bigger, and I want to change that, it's 0.00005 by another 10 to the negative 3. So it's pretty much effectively 0. I mean, most of our calculations, we rarely go beyond 2 or maybe 4 decimal places. So if x is big, the limit when you're dividing by x or by any power of x is equal to 0. And it doesn't matter how big k is, because infinity is going to be much, much bigger than k. So it doesn't matter what's above the line. If you've got x below the line, the limit is going to be 0. Okay, because we're saying what's happening to this function as x gets closer and closer to this value. This is getting much, much, much smaller, so it's getting closer to 0. So what we can do is use that if we end up with our limit as x tends to infinity of anything if we have a polynomial divided by another polynomial. So 3x squared minus 2x plus 5 over 8x squared minus 4x plus 7. So I can't sub in infinity. I can't work out anything for infinity, okay? But what I can do is, so the rule is divide by the highest power of x there is, which in this case, if I look all along the top and the bottom, x squared is the highest. So I divide everything by x squared. And I've got 3x squared divided, so that's 3 minus 2 over x plus 5 over x squared. And then I have 8 minus 4 over x plus 7 over x squared. And now the limit, this is going to get closer to 0. This is going to be 0. This is going to be 0. This is going to be 0. And I'm just left with the 3 over 8. And that function will get closer and closer to as x gets bigger and bigger and bigger. So if you're doing the limit as x tends to infinity, you divide the top and the bottom by the highest power of x. And just another thing about limits is, we've done this without even thinking about it. The limit of a sum is the sum of the limits. So if I have the limit of like 2x plus 3x squared as x tends to 2, that's the same as the limit of, I can split it up, 2x plus the limit of 3x squared. Is that okay? So you can split up limits if you want to. So the limit of the sums is the sum of the limits, the same if it was multiplied or if it was divided. You can just do all the limits separately. So let's just go back and see what else is in the chapter. So we've talked about limit notation. So LIM, short for limit, x tends to, so what x is going towards this number, what's happening to y, or f of x? It's getting close. Is it getting close to a number or not? As x tends to infinity, we're going to have it equal to 0. Slopes we'll come back to now in 1 minute. And we talked about continuity. So continuous means there's no break in the function. And most of the functions we deal with are continuous. But sometimes you can have a break, especially if you have rational functions where the denominator can't be equal to something. Or if you've, anybody remember what this type of function is called? Where there's 2 different parts or more. There's 2 different pieces to this function, so it's called piecewise. So you'd have one formula for x less than 1, and you'd have a different formula for x greater than 1. Well, that would be x less than or equal to. Okay, so if x is equal to 1, we're using the bottom graph because that has the black dot. If x is greater than 1, we're using the top graph, and because that has the open dot. So if it's less than or equal to 1, we're doing this. Greater than 1, we're doing this part. That's called piecewise, and we can see that there is a discontinuity there. Okay, and another word we learned yesterday, an asymptote is a line that graph gets close to, but never actually touches or crosses. Okay, so let's just go back and look at limits, because this is the whole basis now. This little formula there that you're looking at, the limit as h tends to 0 of f of x plus h minus f of x divided by h. Okay, and that will be what we're doing. That's used in differentiating, in differential calculus, in finding the slope of the tangent to a curve at any point. And I'll explain that to you now using this. So if you have a curve, let's just do basic parabola, okay? So the slope of a curve, of f of x, is defined as it's equal to the slope of the tangent at a point, okay, A or x. So if I'm at this, if x is equal to A, then I draw a tangent, which is a line that just touches the curve at one point. Everybody know what a tangent is?
Yeah.
Okay, And the slope of the curve is the slope of the tangent at that point. And you can see at a curve, if I draw a tangent here, it's going to have a different slope. And if I draw it over here, it's going to have a different slope. It'll actually be negative. And what the slopes of those lines actually tell me is what's happening to the curve. So if the slope is negative, that means the curve is decreasing, means f of x is going down. So just by looking at the slope of the tangent, by looking at the sign of it, I can tell if the function is going up or going down. So if the slope of the tangent is negative, the function is going down. If the slope of the tangent is positive, the function is going up. Okay, and so far?
Yeah.
These lines are positive slope, and I can see that the tangent is going up there. This line is negative slope, I can see that the curve is going down. The other thing, like look at the difference between A and say B here. What does the slope tell you? Which slope is bigger there, A or B?
B.
B. Okay, it's steeper, so it's a bigger slope. What does that tell me that's happening to my function? What's happening different at A or at B? What's happening? So we know it's increasing. What does the steeper slope tell me?
It's going up quicker.
It's going up quicker. And remember, we did a whole section on rate of change. So the rate of change, the steeper the slope, the higher the slope, the faster the rate of change. Okay, so that is equal to the rate of change. It's telling me how fast. So it's first of all telling me, is it going up or down? And then the actual size of the slope is telling me how fast it's going up or down. So does that make sense so far?
Yeah.
This is the whole basis of calculus. Okay? It's to do with slopes, and the slope is equal to the rate of change. So let's see where this little function comes in. And it's basically using limits and approximations. So if I have my curve, and I want to get the rate of change. Say, for instance, I just draw between, I don't have the tangent, I just have this line here. So we'll call this point x, and this would be f of x. So the coordinates of that point are, if the x coordinate is x, then that's f of x. And then if we make the x coordinate a bit bigger, so we add on h to the x coordinate. And h is just a random letter that they pick. They always use h, okay? So this point would be x plus h, and then f of, and that value of x, now x plus h. Is that okay so far?
Yeah.
All right. So the slope of this line, remember slope is equal to y2 minus y1 over x2 minus x1. So this is 0.1 and this is 0.2. So y2 is f of x plus h. Does that make sense? y1 is f of x. x2 is x plus h, and x1 is x. Is that all right so far?
Yeah.
So just simplifying that, we can see that the bottom, the x's cancel out, and we're just left with h. Is that okay? Is that all right?
Yeah.
X minus x is 0, so you're just left with h. So that's the slope of that line. Now, if this point is closer and closer and closer to x, so it's moving down so that h is really, really small, then effectively what you have, just sketching it out again, if there's x, if h is right beside x, so small that there's no real difference, now we have the actual tangent and the slope of the tangent. Okay, so what we do is we say h is getting really, really small, so we're getting the limit of that, this here, the limit of the slope, when h is tending to 0. And that's the definition of the slope of the tangent. Okay, so it's the difference in 2 points on the curve when the 2 points are so close together that there's practically 0 difference between them. And that's why limits are important in calculus, because we have to understand. So what we're saying is, what's the what's happening to that line and to its slope when x and x plus h are so close together that h is practically 0. Okay, and that will give us the exact value of the slope of the curve at that point. And if we do it at different values for h, we're going to get different slopes, which will give us the different rates of change at those points. Okay, so it's kind of finishing off this chapter, but starting the next one as well. So example 3 here on page 266. So in the next section of differential calculus, we'll be required to find that. And the reason we're doing that is because it's the limit of the slope as h tends to 0. And that is equal to the slope of the tangent to the curve at any point, which is equal to the rate of change. So for instance, and this is now your first actual time, find the limit. So f of x is equal to 4x minus 5. Now, I'm going to go through the steps for this because this is called differentiating from first principles. So we want to find the limit as h tends to 0 of f of x plus h minus f of x all over h. Okay? Everybody with me so far?
Yeah.
Yeah.
That's basically the slope as h gets to 0. So the first thing is to work out, and I would write them under each other, work out f of x plus h. That's step 1. So what you're subbing in x plus h instead of x here. So that's 4 times x plus h minus 5. Is that okay? And that is equal to 4x plus 4h minus 5. So that's f of x plus h. Next step is we want to subtract f of x. So I would write f of x underneath that. And what will happen is, and you'll be doing a lot more complicated ones, but every part of f of x will have a corresponding part here. So write them underneath. So f of x is 4x minus 5. So I'm going to write the 4x under the 4x and the minus 5 under the minus 5. Okay. And then when I subtract them to get the numerator, so f of x plus h minus f of x is equal to 4x's are gone, the 5's are gone, it's just equal to 4h. Is that okay? You all right so far?
Yeah.
Then the next step, so 1 is f of x plus h, 2 is f of x, subtract them, 3 is divide by h. So that gives us 4, okay? And then we get the limit as h tends to 0 of f of x plus h minus f of x over h. I'm just writing the whole thing out, which is this. So there's no h here. So the limit of this as h tends to 0 is still 4 because it doesn't really care what h is doing. It's not going to change from 4. It's a constant. Does that make sense? And just to relate it back, what kind of function is this? What would the graph of this look like? What would the graph of 4x minus 5 look like? What type of graph is that? What type of function is that?
Straight line.
A straight line. And what's the slope of that line?
4.
4. And what did we get when we worked all this?
4.
4. Now, that's the easiest type of function to differentiate because we can actually tell just by looking at it that the slope of this is 4 and it's not going to change. It's a straight line, so the slope isn't changing. It's constant, and that's exactly what we got. Now, if we look at the next example, it's a quadratic. So f of x is equal to x squared plus 1. I'm just going to go through step by step again. It's important to get these steps in the right order. So we write down f of x plus h. So we're subbing in wherever there's an x, I'm changing it to x plus h. So that's x plus h squared plus 1. Multiply that out. So you've got, remember when you multiply square, you've got the first squared. Don't forget the middle term. Twice the first by the second. So that's 2xh. And then the last squared is plus h squared plus 1. And then we just write down our original f of x under that, lining it all up. So we've got the x squared, and I'm going to write the plus 1 under the plus 1. Make the subtracting easier. Is Now when I do f of x plus h minus f of x, they're cancelled, and I've just got 2xh plus h squared. Divide by h, because that's the next part, and that gives me 2x plus h, okay? That all right?
Yeah.
And then I get the limit of that as h tends to 0, and you can write the whole thing out again. X doesn't care about the h, so that's still 2x. And as h tends to 0, h is equal to 0. So anything with the h in it is just going to disappear. So you'll just be left with that. And that is the slope of this function at any point. So basically, if, let me just graph that for, so what it's saying is the slope depends on x. So as x gets bigger and bigger, the slope is going to get bigger and bigger. Does that make sense?
Yeah.
And if x is negative, the slope is negative. So let's have a quick look at a graph of that function. Sorry. I'm playing with functions with my third year. So if I just graph x of x1, everybody see this on the screen? So x squared plus 1. There's my graph. So at x equal to 1, okay, my function, so then I'm going to graph 2x. So we can see here at the point where x is equal to 1, b is equal to 2. When I go to x is equal to 2, the slope is equal to 4. Okay? It's steeper here. When I go to x is equal to 3, x is equal to 3, okay, my function is equal to 10, the slope is equal to 6. So that's changing at twice the rate it was down here. So the slope is getting steeper and steeper as I go along. And if I'm here, say if x is equal to negative 3, then the slope is the value of the blue line, which is equal to negative 6. So the slope here is minus. So the value of the blue line is giving you the slope of the red function, okay? And all you have to do is sub in. If you want to find the slope on x squared plus 1 at any point, you just sub in. So if I want to find the slope point here, x is equal to 2, so the slope is going to be 4. If I want to find it at this point here, x is equal to negative 2.5, so the slope is going to be negative 5. Okay. And basically what we've done there is differentiated the function. And we will be doing more. That's differentiating from first principles, which we'll get into more in the next chapter. And then we learn how to do it with rules so that we don't have to go through that whole f of x plus h minus f of x by h, etc. all the time. Okay, so I'm just going to give you a few exercises in 7.2 to do tonight to kind of get you used to that, and then we'll get really into it tomorrow, okay? So on 8.2, do questions 7. Do the odd ones, 1, 3, and 5. Question 8. Question. Let's do question 11. Question 12. So that's 7, 8, 11, and 12. If you want to get started on them now, and you can ask questions, I'll just put it up in Classroom when you get started, okay? And I'm just going to take a roll as well. Okay. Sorry, but oh, sorry. Thank you very much. I'm doing chapter 8 with another class. Thanks.
Is it all parts of each question?
No, question 11 is just the odds, but the rest, and then you can do all parts.
All right.
Or question 7 is just the odds, yeah.
Question 7 and 11 are the odds.
No, 11 you do the whole lot.
Oh, okay.
And guys, I'm just giving IXL login details to some people who haven't got them yet, so let me know if you haven't got them. So, Zeph, do you need login details? I know your mic's not working. I'm just going to give them to you anyway. I'm just going down through anybody that hadn't used IXL before, and I'm going to put your login details on yesterday's assignment, so you'll be able to see them there. If you haven't had IXL login details, I'm posting them now to you on yesterday's homework, because it is very handy for practicing and getting the hang of a lot of these things. You all doing okay there?
Yeah.
All right, I'll let you go. So, message me if you've any problems, and see you tomorrow.
Bye. Thanks.
Thanks, Miss.
Thank you.